So, hi. How are you guys? How's week 8 treating you? Yeah? About right. That's about tired. That's about right. Almost over. We're doing well. Well, we're doing well here. I want to analyze that quiz you guys almost finished. Some of you guys already turned it in. That's fantastic. The quiz we were doing in class last time around. I want to recap that up. But JT asked a very good question. He happened upon a random fact online, a statistical fact, probabilistic fact, and I wanted to make sure that you understand how to answer it. So JT, give it to me again. You read that.
If you were in a room with 23 other people, so 24 total, there would be a 50% chance or higher that 2 of you would have the same birthday.
So if you're in a room, you and 23 other people, there's almost a 50% chance that at least 2 of you have the same birthday. If you increase the number of people in the room, that probability goes up surprisingly fast. Now, if you remember, on the first day of class, we did that experiment, and we had a birthday match. I think we had a couple birthday matches, if I remember correctly. I know we had at least one. I can't remember how many we had.
I think we got all the way through those.
We stopped. We stopped before we got to the end. As soon as we got a match, we're like, okay, point proven. But it's surprising, because how many people in the room would you have to guarantee a birthday match? 367, technically. I mean, technically speaking, 367, if you want to be a bastard about it. Because you could have a leap year person mixed in with 365 other people, each of whom are born on January 1st, January 2nd, January 3rd. So it's theoretically possible to have 366 people in the room that all have unique birthdays. But as soon as you throw a 367th person in the room, they have to match one of the other 366. Is that fair?
Yeah.
Okay. Katie's like, yeah, whatever rule. That's why I didn't say it was possible. It probably was possible, not probable.
No, I realize because yours changed.
Because what?
Yours changed.
We were
You're
counting
born in
years.
71.
Birthdays, not birth years, birthdays. January 2nd, February, September. Yeah, I see what you're saying. The years are going to be different, for sure. As a matter of fact, we use that fact, Eric. You bring it up, a very good fact. We use that. Is that not yours, Lydia? Sorry. So we use that fact when we were setting our randomizer. Thank you. When we were setting our randomizer, we use your birthday plus your birth year. But this is just birthdays, not birth years, Pat. This is yours. So, good point, but this is just birthdays. So, you have to have 367 people in a room to guarantee a birthday match. But you only have to have 24 in a room to have it be 50-50. And what's amazing, if you have 40 or 50 people in a room, like we often do on the first day of class, it's something around 90% chance of having a birthday match. Who can sum up the reason why in one quick sentence? And you might not remember this from back in the day, but what does randomness do? Do you remember the word that I used on the first day of class? You might not, it's been a while. It groups, it clumps. Randomness clumps. Randomness doesn't try to spread out. Randomness clumps together. Try this experiment sometime. If you have when you're at the river or you're at a Phil's trail, get a small handful of pebbles and just throw them and let them fall on the ground. And then go look at the pattern it makes. It doesn't make a pattern. There are small clumps of pebbles and then big, vast open spaces. I'd be pleasantly surprised if you threw that and landed in a perfect circle with every pebble equally spaced. Because that's not random. Exactly, you're laughing because that's not random. And the equivalent of that would be walking into a room with people's birthdays perfectly spaced. Just as ludicrous, on a less observable basis. Mathematically, JT, the way you figure out the probability, your project that you're going to do on Thursday works it through with a simulation for you. So when you open the spreadsheet for, I forget which tab it is, I think it's called the birthday problem, it actually simulates what you're talking about. But you can solve it mathematically. What's the probability? What's the probability that no 2 people have the same birthday? Now let's just do this for a variety of numbers of people. You don't have to write this down if you don't want to. This is one of my favorite mathematical calculations, but it's also a parlor trick. It's one of those things you can do at a bar to make a buck. Kind of like bet somebody they can't eat 6 saltines in under a minute. It's a really quick way to make $1 off of somebody. I've done it once. You can do it. It's a theory. I can share it with you if I make $1 a bar. But, so let's suppose you've only got 2 people in the room. Well, if you have 2 people in the room, what's the chance they both have different birthdays? Pretty good or pretty bad?
Pretty good.
It's pretty good they have different birthdays, right? It's pretty good. What's the chance they have exactly the same birthday?
Pretty bad.
1 in 3. Can we use 365 instead of 366 just to make life easier for us? I think that's what 21 would do before anyway. So the first person in the room can be born on any of 365 out of 365 days. So me and Kelly walk into a room, it's just the two of us. She's born on whatever day she is, but I gotta match hers, right? So what birthday do I have to have? Hers. There's a 1 in 365 chance of that happening, correct? But if I don't match her, it's much better. It's 364 out of 365, yes? That means I have a different birthday than she does. What is this mathematically, friends? Can anybody multiply that out for me real quick? If somebody would be so kind. Now, while you're doing that, we're going to keep the logic going. Suppose you have 3 people in the room. What's the chance they all have different birthdays? Well, this would go 365 out of 365. That's Kelly. I want to be different, so it's 364 out of 365. And the next person wants to be different, so they're 363 out of 365. Follow logic there? You see what's happening? Each person I add has to be different from everybody else that was already in the room. Every person I add into the room has to be different than every other person. Now, why is it staying 365 in the denominator? Because it's not sampling without replacement. You could be born on any day of the year, any of the 365 days. The restriction is I don't want you to have the same birthday as anybody else. So, Jen, you have this for me?
0.997.
Well, that's a pretty damn good chance that we both have different birthdays. 99.7%, yes? What's this one here? Do you have this one? Could you just tack a times 363 over 365 on there?
Yes.
Thank you. Thank you very much for your help. I appreciate it. That's okay. Actually, you know what? While you're doing that, let me get Excel going, because we can actually simulate this in a spreadsheet pretty easily. Anybody see the clicker? Did you see it, Don? Oh man, thank you, sir. I have my damn clicker. I appreciate it, Don. Help me out. What's this one here, Jen?
Oh, hold on, I missed that.
Oh, it's okay.
Almost there.
0.99217. Notice what happened. It went down. Not significantly, but a little bit, right? So what I'm going to do, once this thing warms up, let me crack open Excel, and rather than making poor Jen have to do this, I'll make Excel do it for us, based on number of people in the room and the likelihood that nobody has the same birthday. So you can see pretty clearly, if there's a 99.7% chance that we have different birthdays, there's only a 0.3% chance we have the same birthday. 0.3 is 1 in 365. Done. With 3 people in the room, it's not much better. There's a 99.2% chance we all have different birthdays. That means there's a 0.8% chance that we have at least 2 of us having the same birthday. So let me do this real quick for you guys.
So why did you say this was different than without replacement?
Because we're not decreasing the denominator by 1 each time. Once Kelly has been born on a certain day, I'm not taking that off the table for me. I'm allowing myself to be born on that day too. I just don't want to be born on that day for purposes of this argument. That's why I call this a parlor trick, Omar. Because the numerator is acting without replacement and the denominator is acting with replacement. And it throws students for loops all the time. So let's just add, because JT, because you're asking about it, let's do x equals number of people in the room. Okay, make that bigger. Now I'm also going to use a bastard move over here. Probability of no more than 2 people having the same birthday. You know what? Let's say that more logically. Probability of no shared birthdays. How about we do that? No shared birthdays. That makes more sense, I think. Birthdays.
Yep.
Birthdays. Okay, so 2, 3, 4. We'll drag this down. JT, you said it was 23 or 24?
23 including
23, 24, including myself. So we'll go to 24. That includes yourself, right? Probably no shared birthdays. Well, what I need to do is I want to make that expression right there, which is 365 times 364 times 363, and stop after I've done enough people in the room. That's actually called a permutation. It's mentioned in your project for Thursday. You'll see it. If you haven't started the project for Thursday, you'll see it before Thursday. So what I can do is I can use Excel. It's called permute. Yep. 365, that many of times, and I'm going to divide it by 365 to the that many power. Okay, so this might seem cryptic, and I hope it doesn't. I apologize if it does. The denominator is 365 to whatever this is power. 365 squared, 365 cubed. That's what I started that pattern going here. 365 squared, 365 cubed, 365 to the fourth for 4 people, to the fifth for 5 people. Is fair enough?
Yeah.
So that's what that part is. The permutation part, you'll learn about in your project for Thursday. Basically, it starts at 365 and counts down that many by 1 each time. So 365 permute 2 would go 365 times 364. 365 times 364 times 363. 365 times 364 times 363 times 362. It's a way of keeping track of this kind of mathematics. So there's your 99.7% chance, which means we got a very small chance to have a birthday match. Let's keep dragging it down. Same formula. This is that 99.17 that you guys came up with, 99.18. What do you notice as we keep adding people to the room, friends? It's getting smaller. Does that make sense?
Yeah.
Because every person we add to the room, is randomness going to look at the spaces left and try to put that person into the space? Or is randomness going to, it's going to try to clump it. So this is measuring that clumpage. Okay, let's keep going. 10 people in the room. Oh look, it's down to 88% now. 12% chance of a match. 12% chance of a match means, think about it this way, 1 in 12 rooms, each of which have 10 people in them, are going to have a birthday match somewhere. That's what that means over time, on average. Let's keep going. JT says 23, 24, I believe.
24.
Oh, it's actually 23, including yourself. Look, there's your 50%, 49.3%.
No, yeah.
49.3%.
Yeah.
If you include yourself, that's part of the 23.
Yeah, so that there would be a greater than 50% chance.
Boom. Because this is the chance of no matches, which means the chance of a match is actually whatever's left. So after only 23 people, it's switched over so that it's more likely to have a match than it's not to have a match. Isn't that wild? So in class, it's almost a guarantee. Because for you guys, if I remember correctly, I think you had, I'm going to say 40 people in the room that first day. Let's drag the formula down. There was only a 11% chance of not having a birthday match. Which means there was an 89% chance of having a match. I had 8/9 in my favor of having a match that first day, assuming there were 40 people in there on the first day. Almost a done deal. Almost a done deal at that point. Isn't that cool? And it's because every time you multiply one of those fractions, the overall product goes down. And as you go further down, the fraction you're multiplying is getting itself smaller in value. For example, right here, JT, 364 with 365 is not very small. It's close to 1. 363 out of 365 is less than that, which means you're getting it smaller faster. If you work down until you're multiplying 300 over 365, that's significantly smaller than the original ones were. So you're getting smaller and you're getting smaller faster. Look how close it goes to 99%, or look how quickly I should say it goes to 99%.
What happens at 50?
That's what we're going to do. We're going to drag that down, Omar. We're going to keep it going. I love that question. Thank you, sir. So 50, boom. With 50 people in a room, there's only a 3% chance they're all unique birthdays. So there's a 97% chance you got a match. You ever been in one of those classrooms where there's like 60 or 70 people in a lecture hall? It's practically guaranteed you have a birthday match in there. Now, I say practically, because it's never 100%, of course, right? It's never 100%. Until you have, how many people in a room? 366 or 367 if you count leap years or not. And that's what's amazing. You have to have 366 to guarantee it, but 50 will get you 97%. Pretty well, huh? It's one of those parlor trick math. But I don't want you memorizing how to do it algebraically, because it's too much of a unique calculation. Like, it's its own calculation, and it really doesn't exist anywhere else outside of this problem. But the simulation that you guys are going to do on your project for Thursday explains it beautifully. And I think I put 23 people in the room, and I have you simulating those rooms. And it shows up roughly half the time you had a birthday match, and half the time you don't. Famously, Johnny Carson had a guest on. This is going back, I don't know how many years this is now. He's dead now, but he was a late night talk show host. And one of his guests had heard this and was trying to explain it to Johnny Carson. And he said he tried to do his best job. JT explained it perfectly, by the way. And Johnny goes, I don't believe it. And the guest was like, well, you don't have to believe it, try it right here. And he's like, okay. Johnny's birthday, I think, was October 15th. I'm making that up because I don't remember. I think it was October 15th. And he goes, how many people in the audience have a birthday on October 15th? And his audience is about 200 people. 200 people? Shouldn't there be a birthday match? Good Lord, 99.99%. But nobody matched Johnny's birthday. So was that just a fluke occurrence?
People were too shy to raise their hand.
Say that again. Oh, I would hope not, but let's suppose they weren't. Sarah's got a good, maybe people were too shy to raise their hand. But let's suppose they weren't. Let's suppose nobody matched Johnny's birthday. Does that disprove what we just did?
No,
No, why?
because it's not matching your birthday, it's matching a birthday.
It's matching a birthday, of which there are 365. Nobody said it had to match October 15th. We said we have to match a birthday. Not necessarily Johnny's. How about his host? Did they check his guest? Did they check his guest's birthday? No. Did they check the first lady in the first row in the first seat? No. Did they check the second lady in the second row in the second seat? No. They checked one birthday and didn't have a match, and Johnny threw out the window. And the poor guest was flabbergasted. He couldn't explain it any better. He couldn't or just sum it up in 2 sentences. No, you didn't disprove anything because you didn't check every birthday. What they should have done was what we did. Now, they would never do that because it's network television. They wouldn't take the time to do it. But, who was born on January 1st? Or January birthdays, and, 80 hands go up. Well, right there, if 80 hands go up in January, you've got to have a birthday match, right? There's only 31 days in January. If you've got more than 31 hands up, you got a birthday match, don't you? Does that make sense? Everybody seeing the logic there?
Yeah.
So poor Johnny and his guest got it all goofed up. But you understand it now. Beautiful. Absolutely great question, JT. In case this is all kind of like, when you do your project for Thursday, it's revisited. It's a great problem. And I like revisiting it twice, a little bit algebraically too. So thank you for that question. Fantastic. Cool? Good. Please, I know we have very limited time left with each other. But if you guys do experience stuff like that, you come across stuff online, bring it into class. I love that. I love, starting class with that kind of stuff. Good. All right.